All right, up next we have David Jack DeGeneres, and he is doing the reporter for Group 1, Experiment 3 as well.
Hello, my name is David DeGeneres, and I will be explaining the ranking cycle that we were supposed to do last week. Start off, we didn't actually do it last week, so didn't really get the knowledge that I was hoping to get from doing the experiment because we had a boiler failure. Basically what happened was, you can see all the rust. It's hard to see in the picture because of the lights, but it's real dark and rusty. See here. Basically one of those tubes had a fracture in it because they didn't heat treat the welds right and caused it to flood a leak. Therefore, it wouldn't hold the water or the pressure, and therefore we could not do the experiment, which was kind of unfortunate because I think it would have helped a lot doing the calculations. But another class was nice enough to give us their data. So this is the graph of fuel flow versus time. And you can see it stays pretty consistent, slight erratic, but I mean it's between 5.65 and like 5.7. So really not that much of a change, but you do see that it increases when you're actually trying to heat up the water. This is the boiler temperature versus time, and you can see towards the end that it starts to increase almost 500 degrees Fahrenheit, and then time is in seconds, obviously. And then this is the boiler pressure, which remained constant for them, right around 110, which allows you to get more of an ideal cycle, which is what we are looking for. This is the ratio of the inlet to outlet pressure of the turbine, and you can see it's not the prettiest looking graph, but that's what you get. Don't really know how to interpret that because, like I said, we didn't do the experiment. This is the inlet. This is the temperature ratio of the inlet pressure to, or the inlet of the turbine to the outlet. As you can see, here is going through the cycle, and you can really see where the water is entering the cooled state versus the heated state. This is the current output generated by the generator, like the turbine generator. You can see it remains pretty constant with a slow, steady increase as the cycle continues to keep going. I believe that's because as more and more water is burned off, you have less water to heat up. And then this is the voltage versus time of the turbine. And then you also have the RPMs, as Johnny pointed out. They're pretty much identical, minus obviously the units that it's measured in. So the RPMs directly relate to the voltage created. And then basically what we wanted to do was find the thermal efficiency of our system as the ultimate goal. Basically, you want to use an ideal situation, H3 minus H4 plus H1 minus H2 over H3 minus H2 gives you the efficiency. You want to find those enthalpy values by using the steam tables provided in, if you have your thermodynamic book still, or you can find them online. And you go through, you use what you know from the data provided from picking a steady state position, use the known pressure, the known temperatures to figure out what those enthalpy values are to calculate your efficiency. And I got 71.5 for the ideal cycle, which is not too bad. What you want to do though for ours, since it's obviously not ideal, you lose some water in the system due to condensation, doesn't go back through. You also lose heat in the piping as the steam's going around. So you want to use Q equals m dot Cp delta T. And you use, again, once the data provided at certain locations for like the inlet of the turbine versus the outlet, calculate that delta T and use the Cp. And once you do those calculations, I got about 70.2% efficiency, which is obviously less than ideal, is what we expected. And obviously the system was designed to be as ideal as possible, but since we can't get perfectly ideal, that is what we ended up with. And that is all I have. Does anyone have any questions?
How much fuel did you say you used again? Like, what were the values between?
The values were between 5.65 to 5.72 is like the absolute highest liters per minute. So, I mean, it stayed pretty consistent mass flow across, and actually I use that whenever you're doing the heat added in by the boiler to calculate the efficiency. I used that as the mass flow rate of the fuel, and I kind of picked a steady state, which was kind of around in here, because you can see it's more, like that would be more linear than obviously like that. So I kind of just picked a point somewhere in here. It came out to be like 5.6, like 85 or something, and I used that to calculate the Q added, which is what you need to calculate efficiency. Any other questions? Thank you.